Hello, everybody, and welcome to today's webinar, Just How Dangerous is Hydrogen? I want to thank you all for taking the time to be with us today. I hope you find it useful. My name is Chris Coffey. I'm the product manager for our software product Flax, and in particular Flax Hydrogen. But today I'm playing the role of moderator in today's webinar. We will be running a Q&A at the end of the webinar. So we've enabled our Ask a Question feature. You should be able to see it on the right-hand side of the screen. So if you have any questions, feel free to pop them in there and we'll do our best to answer them at the end of the webinar. And if you miss anything, please don't worry, we're recording this and we'll send out the recording to you all afterwards. So I think now it's time for me just to hand over to Geirmund, our speaker for today. Geirmund is our Vice President of Hydrogen Safety here at Gexcon, and as such has been involved in many hydrogen-related products. So I'll hand the floor to him and let him take over. Thank you.
Thank you, Chris, and I can reiterate Chris's welcome to you all, and thank you for taking the time to join us today. The presentation today will be focused on where we are in, well, the physical properties, our summary of R&D activities, some inputs to design practices and design verification. We're also going to describe an investigation of an incident and then go on to Q&A. So you may or may not know that Gexcon have been in the market for quite a while in terms of experimental and also prediction of how accidents evolve, particularly fires and explosions. We have been involved in many projects concerning hydrogen over the last around 20 years, and we've worked in several different industry branches. As I said, a lot of experience in large-scale experiments where we've run experiments with up to 50 cubic meters of hydrogen. We'll get back to that a bit later. And also, we've developed and commercialized Flax Hydrogen, which is well, Flax is an acronym for Flame Acceleration Simulator, and we have a module in there that's validated and set up to match the physical properties of hydrogen to the best possible level of well, accuracy. We are currently involved in several projects on electrolysis, liquefaction plants, methane steam reforming, maritime applications, metallurgy, nuclear industry, fueling, and investigations of accidents. So we are quite a broad provider in the hydrogen safety business. When it comes to hydrogen, it's just different from many other substances that we used to deal with in terms of chemistry and fuels particularly. It's a lot lighter than air and will rise very quickly compared to natural gas. It's got a very wide flammability range from 4 to 75%, so it's quite difficult to manage in that respect. It will leak easily because of the small molecular size. The laminar burning velocity is high, it's quite reactive, so it's about 6 times faster than hydrocarbon gases in terms of flame velocity. The ignition energy is low, about 0.2 millijoules. Under pressure, that drops even further, so it's quite easy to ignite, but it has a high ignition temperature. There's a negative Joule-Thomson effect. That means that it will heat up when it's released from a high pressure. That, coupled with other effects, may be reasons for a tendency to auto-ignite from high-pressure leakages. I'll get back to that a bit later in the presentation. In terms of where we are with R&D, we've had this substance in the industry for more than 100 years. It's been widely used as a syngas in industries, but not so much in terms of fuel. But we do have quite strict safety regulation in the industry for most of the industry. Whereas when we bring this into society, there may not be this environment where we can impose that kind of strict regulations and controls. So we need to have a good design, we need good operating routines, so we need to understand how these physical characteristics of hydrogen actually influence how we can deal with it. So it's not a man-machine interface, it's a chemical machine, man-chemical interface, as it were. And we need to be able to accurately predict what happens if we lose containment. And we have had and will maintain the ambition to have a leading role in the research into that kind of question. This is the project that was run by the European Commission. HYSE is hydrogen in what's that acronym? Hydrogen safety in energy applications. I'm sorry. It's a project that was run by the EU Commission, and we Gexcon ran the project we executed for them as a project coordinator. The idea was to look how we could implement hydrogen as basically a fuel by being able to predict what would happen in a typical compressor station that you would see in a fueling applications. You need to bring the fuel up to a very high pressure, because the pressure in a normal tank in a car would be somewhere around 700 bar. So it's about how we could model this. Has been quite well known how hydrogen behaves in an open space and in a non-congested explosion. That's quite well known, but in a congested and maybe a vented explosion, it's not that well known. So in order to find out how to deal with this, a test setup was established. Is a 20-foot ISO container with a mock-up of a typical interior. This is a depiction of some pipes in a rack. These are basically bluff volumes and no real equipment, but we had a few different interiors that we could build in this container. Also, there's a frame in the ceiling where various configurations of venting devices could be fitted. So in all, we had 65 explosions in 20-foot containers in concentration of hydrogen up to 25%. This particular video you will see now is a 24% unvented explosion, and this is what happened. Let's see if we can make this play. Now you will be able to see it. Sorry about that. So again, 24%. And you can see doors and parts flying around. And we also shot all the experiments with a high velocity camera. So as you see, the walls buckle almost like a paper bag. Wow. I think I've got this all wrong now. Okay, sorry. Back to the presentation. So this was the unvented version. The next slide is with a video with a similar concentration of hydrogen and plastic folders to mimic vent devices. And there was hardly any overpressure at all in this experiment. So if we look at that video, that should be here. So as you can see, there's hardly any deformation of the walls, and these plastic venting devices went off quite easily. We also did a number of experiments with commercial venting devices as well. But these two were sort of the ends of the spectra. Okay, so a lot of publications have been made on this, and it's all available under this www.hic.eu. There's a large number of publications made on this project from ourselves and from other participants too. In 2018, it was found that with mixtures of hydrogen and nitrogen, the flax coat underpredicted the laminar burning velocity of these mixtures. So we conducted a literature search and also put together an experimental campaign to find what happened and try to overcome that weakness in the code. We did get a pretty good test series, and we actually had some of the tests going off to full detonation. It also proved that our test had a very good repeatability. So this test data was then coupled with validation database that we have for Flax, and we have now upgraded the software to include this feature. And just a quick view of one of the experiments where we see a high-speed camera of one of these explosions vented to one end. This is a 50 cubic meter vessel, and let's see, slides, back to presentation. Yeah, so it's roughly 20% of hydrogen in there. I don't know what's the exact composition, I'm afraid. I can find out. Right, in the coming year, we'll be using a lot of energy towards SHIFT, which is a project that really is focused on improving the competence and safety of both gaseous and liquid hydrogen. There will be some new modeling development. There will be large-scale fire and explosion experiments, and also RPTs and BLEVIs. So we will actually then pour liquid nitrogen onto a steel plate, onto water, and we'll also try to make a fire under a liquid hydrogen tank of roughly a cubic meter and see what happens if we can develop a BLEVI. Those tests are planned later this year in Germany. We do have a test site in Norway, but that's not big enough for a BLEVI test of hydrogen. So we try to find a larger site for that kind of experiment. We are also part of a project called PRESHNY, which is again an acronym for Pre-Normative Research of Safe Use of Liquid Hydrogen, primarily focused on again finding solutions to some of the modeling challenges related to release, ignition, and combustion of liquid hydrogen. We do know that a liquid release will be very cold, but the question is, will it form a pool? If so, will the pool? How does it evaporate and burn? Or do you just get a cloud of flashing hydrogen? That's really not very well understood currently. So we need more information on that, and this will also then provide an input to international standards within this field. And this is a video that we have which shows. Again, it's a test from the HIC project, and how these findings and results have been implemented in the FLAG software. So it's basically a demo of a test and a simulation of the same issue, and it's pretty good agreement between the experiment and the simulation, much to our joy, I must say. So that's where we want to go with all the experimental work we do. We want to put it into the prediction tool so that we have a good understanding and way to model what happens if and when we have a loss of containment. The Road Administration Norway had a series of tests earlier this year where they released liquid hydrogen. This is because there's a project on to build a ferry that will be hydrogen electric, will go into operation next year. So the steelwork is well underway, and also the system design for the hydrogen system. In order to benchmark and gain more knowledge, the Road Administration gave the work to DNV in Spedalem to do some tests with the release of liquid hydrogen. It was also involved DSB and the Defence Research Establishment in Norway. These results, the tests have been performed. I've basically just heard of the initial results, but they will be published at some point later this year, probably within a couple of months, is what I hear. And we eagerly await the results from these tests. We haven't been allowed to discuss them further, I'm afraid. So the question then is, with all this research, do we know what we need? And the answer is no. There are still a few gaps within the knowledge that we have, and we want to be a part of filling those gaps. There's the issue of jet fires, as I said, formation of liquid pools, evaporation and fires from liquid pools, the transition from deflagration to detonation. Have a really good understanding of that, and also the correlation between reservoir pressure, aperture geometry, and leakage rate, to try to gain an understanding of the probability of spontaneous or auto-ignition. But to date, FLAX is the only CFD code that's validated for hydrogen, and we are continuously working to improve that software and keep it validated and provide good predictions also in the future. A little bit back to the issue of spontaneous ignition. It's been known for decades that this can happen, and especially with high pressure leakages. But do we really take it into account? And we are now looking at implementing hydrogen as a fuel to cars, which will have a 700 bar storage pressure on board. That means that the fueling is driven by pressure difference, so the fueling storage needs to be even higher in pressure. So probably above 900 bar, which is a really high pressure. Now, we know that with a high pressure leakage, this can occur. We just don't know why. There are some hypotheses, but they have never been really well confirmed. Brian Maxwell and Matteo Radulescu proposes that this is due to some hydro or dynamic shocks, fluid dynamic shocks. And in these shocks, there may be high concentration of energy, i.e., high temperature, that would bring on ignition. There's also something about corona radiation, which is also described. And the question is, does the leakage geometry play a role in this? So how do we design our sealing systems? And going left to right, these are very different, and the leakage paths would be very different from between the three designs, and do these designs have any influence on the likelihood of autoignition? We probably need to find this out, and for now the research into this has not been carried out to a level where we have a correlation between the storage pressure, the leakage rate, and geometry, so that we can effectively make a prediction of what the autoignition probability would be in a high pressure storage system for hydrogen. So how do we go about designing our system? Now, it's just a short sort of note on good ideas. Keep natural ventilation where possible. Mechanical ventilation have a tendency to break down, so if we can make this naturally ventilated, then at least we have the ventilation option available to us at all time. Avoid the possibility of accumulating in the buoyant gas, so any high points that can trap gas should be avoided. The site congestion is also an issue. Try to, as we know, any obstacle will speed on an explosion. So any obstacle would act to increase the velocity of the flame front. So if we can keep the congestion and geometry complexity low, that gives an ignited cloud less opportunity to increase the flame speed velocity, and could prevent these really severe detonation cases where you get explosion pressures excess of 15 bar, which is quite dramatic. Detection of leakages. Yeah, back to keep the potential leakage sources limited. Try to go fully welded and group potential leakage sources where they are easily detected. And detectors could maybe be augmented by improved control system algorithms. Any trending in pressure and so on could maybe be used to detect small and latent failures. Fully paved areas under pressurized systems and with concrete primarily, not asphalt. Also under cryogenic systems, avoid asphalt. There you can use concrete or large pebbles, and preferably below cryogenic storage, you would add a slope so that if there's a liquid release and pools may form, they will actually run away from the tank, so that you will limit the chance of a fire under the tank. Ignition source control, obviously the de-energizing of any equipment if you get detection, and also ATEX gas group 2C temperature class 1 would be the appropriate ATEX nomination. And also maintenance and inspection procedures are important, as the sealing, the tendency for things to go wrong may be a bit latent, so it probably requires a different approach to inspection and maintenance, and obviously suitable training of personnel that are to operate your plant. That's important too. In terms of verification, it's mostly the same as what you do for a normal process plant. Hazard identification, so that you capture all risks. Hazard and operability studies, so that you will verify that any deviation from normal process conditions can be detected and prevented, so that you can prevent development into a hazardous situation. Ventilation and dispersion studies to support the size and location of flammable clouds in the event of leakages, and to what extent ATEX zones and locations for detectors could be suitable. and also fire explosion modeling to verify events so that risk can be controlled. And that would also go into the QRA that's normally needed when you establish a hydrogen processing plant, because you will very easily get over the 5-ton limit that would mandate, say, Seveso type risk analysis, so that you can demonstrate that you will not have any domino effects towards neighboring facilities. This video is a depiction of a forced ventilation where you have a release, and how that release is then diluted by the ventilation. The release happens in the lower story and moves through an opening in the floor, and is then evacuated by the AJAX system. So this is the kind of output that flux hydrogen will give you, and you can, at any point, you can freeze a cloud and ignite it at any location, and then you would model the resulting explosion from that point. There. And then, given a cloud, you can then model the explosion. And this is how it looks. See? So you can get peak. Here's the yeah. You can see both concentration and heat load and pressure and whatever you want to see from those explosions. Let's go back to the slide. Okay. So in June of last year, there was a leakage and subsequent explosion in a hydrogen fueling station in Sandvika in Norway, and there was several fires following the explosion. We were called to investigate root causes and the incident, propose mitigating measures, and how they could be implemented in future facilities. After looking through all the debris and disassembling much of the plant, we found that on the tank which had leaked, this was a tank where the pressure was 950 bar, and at the onset of the leakage, within 3 seconds, the pressure dropped by more than 100 bar in the system, probably lower in the actual tank. And we found that these inner bolts holding a bushing were under torque. They could be opened more or less without a tool, and they should have had a tightening torque of somewhere around 90 Newton meter. So we also tried to find other possibilities of the root cause, and one by one they were ruled out. So the mechanism we believe have caused the leakage was that these bolts on the inner ring were under torqued. That means that the O-ring, represented by the red circle on the drawing, had insufficient compression. And then as you fueled cars, there would be a pressure cycling of the tank down to about 700 bar, back up again to 950, and that would happen every time you fuel the car. And that means that since the ring was not sufficiently compressed, there would be motion in the ring, and that would have caused friction and wear. Initially, a small damage occurred, and eventually that developed to a full failure of the O-ring. This is also then underpinned by a trend. We could see that this particular storage lost pressure very slowly compared to a neighboring storage that held pressure quite well. So this pressure was dropping a bit faster in this storage than on the other. So that's an indication that there was a latent failure in this O-ring. So once the leakage occurred, it would have been somewhere around 1 to 1.5 kilograms per second. And we looked at various mechanisms for ignitions, including spontaneous ignition, agitation of particular matter. It was gravel located under the storage, exposure to non-ATEX mechanical or electrical equipment. And all of those above mechanisms would have had a potential to ignite the leakage. The evidence at the site was, well, due to extensive fire damage, we couldn't really find hard evidence of any of those. It was deemed, though, that auto ignition had the potential to be a likely mechanism. But since we couldn't find the evidence for one single ignition mechanism, we proposed mitigating measures for all the four above. So they were communicated to the client. The gas was dispersed to several parts and via under the wall or in, well, there was some openings between the compressor room and storage. The storage then leaked. The gas leaked into the compressor room, and once ignited, that caused an overpressure and an explosion in the compressor compartment. We also had some free air. The free air hydrogen that was basically just dispersing into free air also caused some. Well, it burned violently. Whether that would be a flash fire or an explosion. Indicatively, there was some broken windows and released airbags in the area. So it indicates that there was a pressure wave that was caused by this combustion of hydrogen. So whether you call it a flash fire or an explosion is I think it's semantics, but it did throw off some architectural elements on the perimeter wall, and we also had these cars that were affected. And this image here is a result from the simulation of the explosion internal to the compressor module. And then there was some fires, and the smoke you see in the fire in the picture on the right is from a composite tank storage that was adjacent to the compressor module, which was ignited by a fire that probably originated in the high pressure storage and formed a jet fire that burned through an aluminium frame and melted the inner lining of the composite tank, so that the hydrogen then permeated through the composite material and burned off from the outside. After the event, the pressure in these tanks was gone. So most of that hydrogen in those tanks was spent by this fire. And the smoke is generated from the burning polyester, so that's not coming from any hydrogen. And you can see these black panels on the ground here. Those are architectural elements that were on the wall originally that were thrown off by the original blast. So, learning points. What did we learn? We need a documented and verified mechanical completion. This would have detected the under-torquing. We need better testing regimes. We need a wide use of ATEX equipment. We need a smart control algorithm that would have detected the deviation between the two storage banks. We recommended to redesign the vent system. The vent system was partly destroyed by the event and caused the relief valves on the remaining high pressure storages to dump its hydrogen into the compressor station after, and that also caused a big fire. The fire partitions, firewalls are effective. That's a big learning point. If we go back to the previous slide, it's hard to see, but here are the composite tanks, and there are some metal tanks on the backside here behind the firewall, and we couldn't even find bubbles in the paint on those, so they were quite well protected by the firewall, and that really matches the knowledge that hydrogen fires give off little heat radiation. Fail close valves in the facilities had aluminium actuator housings. They melted in the fire. So if you want a valve to be fire safe, it needs to have a housing of another material than aluminium. Hard surfaces under all pressurized equipment, and also cable trenches should be filled with sand or other stuff that would prevent the migration of the event. The compressor module had a relief hatch for internal explosion, probably undersized, so that's a recommendation. And also, we would recommend to install fire water headers as dry sprinklers, so that the first responders can connect to a single coupling and provide water to cool all the parts of the facility if you have a fire. Obviously, if you have a hydrogen fire, it's probably better to cool things than to try and extinguish it, because then you could have the formation of a cloud that could later form an explosion. So that's not the right approach if you meet a fire. So back to the question that we posed originally: is it just how dangerous is it? Well, it's clearly different from other fuels, so we need to handle it differently. And our mission is to enable the industry to gain the knowledge and develop designs and operating procedures so that hydrogen can be implemented in society without any increase to employee or societal risk. So that's our mission, and we believe that's possible. So, Chris, I think I'm going to hand it to you for the Q&A side.
Thank you, Geirmund. We have had a few questions on the chat, and if anybody's got any more questions, feel free to keep adding them. The first question I can answer myself. We've had a few questions about whether we'll be making the presentation available. I can confirm that we are recording this, and we will make it available to everybody shortly after the webinar. On to the questions for you, Geirmund.
Yes.
A question regarding at what point during the project development do we need to do CFD modelling? So at what point in the lifetime of a project do we think it's appropriate that we need to do CFD modelling?
Well, in the initial siting of the project, you need to have a handle on whether you will have to have any problems in gaining the approval to operate, right? So for that kind of screening risk analysis, I would use the multi-energy method just to gain a sort of idea where we are. But when you get to the actual permitting and you need to submit a QRA for that, then you probably need to do CFD modeling, especially if you're if you're looking at a fuel station that is going into an urban environment. Then there's going to be buildings and structures around that could affect the ventilation and how the hydrogen disperses. So I would recommend to do it then, at least. And also, if you look at if you want to do parts of the facility which are enclosed, any enclosed space, I would do a CFD to see that we actually can bend everything, and if things are ignited, what will be the effect of that? So you need to, if you need to define weak areas and pressure relief or explosion relief devices on the enclosed area, I would say that you would have to do CFD.
And I've just seen a follow-up question, which I might answer, asking who should perform the CFD. Does it require an expert user? As the Flax product manager, I can say that obviously Flax is easy to use and it's a very usable piece of software. However, as with all these things, it's the engineering knowledge that's crucial. So the use of the software itself is relatively straightforward, setting up the scenarios, running the scenarios, and getting the results out. But it's understanding what are the appropriate scenarios to run and interpreting the results that requires the expert level of knowledge.
Yeah.
So to move on, we've had a few questions asking about, in some of your guidelines, you asked whether you said that asphalt should be avoided under cryogenic storage, and a few questions asking why that might be the case. You could expand on that.
It's got to do with the embrittle. Well, asphalt is not a hard. It's more like it's like a liquid. So it's sort of metamorph material, and it cracks up very easily. So it will contract and create cracks, basically. So you don't want that. You want it to be a harder surface. And also, you can get some reactions with the hydrocarbons in the asphalt.
Okay, thank you. A question relating to the HYSEA project.
Yes.
And whether there was various findings from the HYSEA project, or whether those have yet made it to design codes or standards, particularly for refueling stations and the like. Are we aware of that yet?
I would have to reverse on that. I don't want to take that from memory. So we'll save that question and we'll try to answer in writing, I think, if that's okay. Yeah.
We've just had a couple of questions just asking to clarify. We've fallen into using some acronyms, perhaps.
Yes.
So CFD is computational fluid dynamics. So that is where we solve the full three-dimensional geometry and use to solve the equations of fluid flow and combustion and what have you, as opposed to the tools like Fred and Effects and FastEven, who are solving empirical type relationships. And then the second question is, what is QRA? QRA stands for, go on, you take it, Geirmund.
Quantitative risk assessment. So it's basically a summation of all the events that can go wrong, what frequency they would carry, and what consequence it will have. So it's a summary of all of that. So you can then take all the scenarios, all the effects, and calculate to potential loss of life per year or individual risk per annum for individuals and so on. So it's basically it provides a measure of the risk of loss of life, basically.
As a follow-up, there's a question asking whether Flax, the CFD code Flax, has a QRA module. And indeed it does. It has a module called Flax Risk that allows you to include that frequency information to combine the consequent results from the CFD into a risk picture. Can I look through the chat? There's a lot of questions in the chat, and we probably won't be able to get to all of them, I'm afraid, but we'll do our best.
Yes.
One question about siting of facilities, and whether there are regulations to help with siting of facilities in terms of Obviously, the accident you showed was very close to a road.
Yeah.
Maybe you can comment on that, Jim.
Well, there are rules for this. Primarily, the mothership of those regulations is in the European realm. It's the Seveso 2 regulation, and in the US, it's an NFPA regulation. I can't quite remember the number, but the NFPA has a standard for this. So that's the regulatory framework that we're working on. And basically, it's the intention of these regulations is to limit the risk for third parties. So anyone, sort of bystanders or passerbys or whatever, should have a very limited risk of losing their life if there's an accident. So that's the basis for that kind of zoning. And in siting, you usually have 3 different zones around a facility. It's the sort of inner zone, that's the facility itself. Then there's a sort of middle zone where you can have passing by, but no shops or any houses or anything. So it's sort of a clean zone without any. There may be commercial activity, but no housings, no schools, nothing. And then there's the outer zone where you may have houses, but not hotels or schools or homes for the elderly, or what would it be? So there are 3 sort of layers, and when you get to the quantitative risk analysis, you actually the limits are then coupled with a frequency. And in Norway, at least, to be in the outer zone, that's a risk control for 10 to the -7 per year of individual risk, which is very low. So the regulations are actually quite strict. That means 1 per 10 million years of loss of life. So it's almost like the lottery in terms of the probability of being severely affected by an accident. Yep, I see now there's someone helping us here. It's the NFPA 2 hydrogen code. Yeah, in the US. So thank you for that.
A question regarding your comment on the heat radiation from hydrogen fires versus hydrocarbon fires. Maybe you could expand on that a little bit.
Well, yes, it's really quite astonishing. We had this large fire. Well, literature says that there's not much heat radiation from hydrogen fires, and it's something you read and you sort of believe it. But when we visited the accident site in Oslo, we found that just less than a foot away from this really intense fire, from this initial leakage, there was not even buckling in the paint. So, and that's less than a foot from the flame. And if there was if this was had been a hydrocarbon burning, it would have generated a lot of heat. But in hydrogen, there's no carbon. So in a hydrocarbon or wood or whatever fire, you will have carbon particles in the flame that are heated, and then they, according to Stefan Boltzmann's law, they will have a heat radiation which is proportional to the temperature to the 4th power. But in hydrogen flame, there's no particles. There's nothing. There's just water. So there's no substance that gives off radiation according to this Stefan Boltzmann's relations. So that's why. I mean, that's a physical reason why there's not much heat radiation from these flames. And it was really extraordinary to see it in real life how unaffected items that were only a foot away from the flame was from the fire and the heat load. that was a bit of a was learning by looking. Yeah.
Great.
I hope that shed some light on that.
I think so. I think so. We've probably got time for just a couple more questions.
Yeah.
Are you able to comment on detection of hydrogen in terms of detection devices?
Yes. They are slow. You usually use a hydrogen detector is cathodic detection usually, and the response time is actually quite low. It's high. Response time is high, so it's usually around 4 seconds to actually respond to detection. So I would say that this is something that should be looked at in terms of design. Can we devise smart algorithms in the control system that might help us and give some pre-warning? Can we use thermography, for instance? Can we find other ways to detect this? Because 4 seconds in the event, in a normal event, is actually quite long. When we look at the incident that we investigated in Oslo, from the onset of the leakage to the actual ignition, we estimate there was 3 seconds. So a hydrogen detector wouldn't even see this before it all went wrong. So we need to find better ways of detecting leakages. We need to find better ways of having pre-warning and indicative measurements that can tell us that something is en route to becoming a problem. And we need inspection routines in addition to the detection systems, so that we can find these problems before they actually turn into an accident. So it's a bit of it's quite a bit more difficult than detecting hydrocarbons, and that's with the available technology.
Okay, I think maybe time for just one last question that kind of wraps up the view of is hydrogen or just how dangerous is hydrogen. A couple of questions
Yes.
being asked about. Obviously, there's a lot of thoughts at the moment about replacing natural gas for heating in domestic. So certainly in the UK, we're looking at having it in houses. I think the question is just wondering what your position on using hydrogen in domestic premises is.
Well, if I've read the literature right, it's a mix. It's actually a question of mixing some hydrogen into methane. So it's not pure hydrogen as such. So if you want to burn this in a burner, you probably need that kind of mixture, because a hydrogen burner is not really that well developed. If you want to do pure hydrogen, you probably look at using fuel cells and convert to electricity, and then use the electricity, which is then a completely different prospect as such. But it needs to be done in the right way. I mean, if you have a hydrogen distribution system that's mostly outside the home, that's fine. If you have a leakage, you would have to have an isolation valve outside the home. The inventory of hydrogen that would be inside a domestic house would be very low. I mean, in the matter of grams maybe. So you wouldn't see any big severe events from that. So you would have to find ways to limit the amount that would be in a house, and to find a way to easily shut down if you get a problem. And inside the house, I would say that any pipe would have to be double walled, so you would be any leaks would then just go into an annulus around this pipe and be vented somewhere. So there are ways to handle this, but it has to be designed in just a different way than the normal domestic gas system. So you would have to do significant rework to the domestic systems, I would assume.
Great, thank you. I'm afraid we're out of time now. We've reached our time. The questions are still piling in.
Yes.
So I hope you all found it useful. We will make the recording available, and we will look through your questions and see if we can provide further answers or if they can inform future webinars. This is the first of many webinars, we hope, not just on hydrogen, but on various topics around risk and safety. If you have any suggestions for things that you would like to hear us talk about, then please just do get in touch, and we'll see what we can do. But until next time, thank you very much for taking part, and we'll see you soon. And stay safe, everybody. Goodbye.
Goodbye now.